Numbers are a critical part of the way we understand our world, yet we are still uncovering their secrets. In this video series, I would like to explore numbers, but not just any ordinary numbers. We are going to explore big numbers. Last time, we learned about the outrageously large Graham's number, one of the more well-known large numbers, described by Ronald Graham in the 70s. Graham's number is truly enormous and can be written out only by using recursive formulas, such as using levels of Knuth up arrow notation, as shown here. So far, we have discussed several massive numbers, each dwarfing the previous number. At this point, it is useful to take another step back and think about how we are describing large numbers and how we generate them in the first place. If you think back about the numbers we have described, a common theme you find is that large numbers come about when we have to change the way we are counting. And so to think about large numbers, it is helpful to think less about the size of the number itself and instead think about how quickly we are able to reach these massive numbers. This brings us to what is called the fast-growing hierarchy, or FGH, which is a way to categorize how rapidly a function can generate large numbers. We can build this hierarchy as follows. Consider the function f0, which is called the successorship function. This is the most basic growing function and merely adds 1 to the previous number. This can be thought of as our addition-style growth function. The next function, f1, is equivalent to the f0 function carried out through n iterations. Under the hood, it looks like this. But to summarize, we can think of this as our multiplication-style growth function. So far, these functions aren't growing very quickly, but you might be surprised how soon we pick up speed. The next function, f2, iterates the multiplication-style growth function to give us an exponential-style function. This grows more rapidly, but still doesn't reach any large numbers very soon. The function f3 is where we really start to see some explosive growth. This is our tetration-style function, and we very quickly are able to reach some big values. In fact, f3 of 5 is larger than Google, and f3 of 6 is larger than either Googleplex or Skew's number. These functions can continue building in this fashion, where each function iterates the function before it. These functions very soon describe very fast-growing number sequences, but it's still not quite growing fast enough. Even at a ridiculously high function number, it would still take an outrageously long time to reach numbers as large as Graham's number. In fact, there is no function in this sequence that reaches Graham's number quickly. But we are not done with the fast-growing hierarchy. Using finite numbers is actually only the start of the fast-growing hierarchy. We can actually move to a new sequence by employing a technique called diagonalization. It works like this. The f2 function grows slowly, whereas the f3 function grows moderately quicker, and the f4 function grows much faster. However, if we look along the diagonal of these values, we get a function that grows faster than any of them. This diagonal function can be given a new definition. F omega is equivalent to the function fn of n. And just like the beginning of the fast-growing hierarchy, we can add 1 to omega to get a function that iterates the previous function. Let's see what this looks like. F omega plus 1 of the value 2 is the same thing as 2 iterations of f omega. To evaluate the inner f omega of 2, We simply replace the omega with a 2, and then this should look familiar. This is an exponential style function, which gives us a value of 8. We then evaluate the outer f omega, where we replace this omega with an 8. Now, this is a nonation style function. This uses 7 arrows in Knuth notation. This is a pretty massive number, and we are only at 2. F omega plus 1 of the value 4 gives us a value that is larger than Moser's number. And if we compare it to Graham's definition, we see that F omega plus 1 of the value 64 is actually larger than even Graham's number, which means that F omega plus 1 is now the fastest growing number sequence we have encountered to this point. The fast-growing hierarchy can be used as our measuring stick to investigate not only large numbers, but the processes by which we reach these numbers. It gives us a powerful new tool and new language with which to describe the world of large numbers we have been exploring. Now, you may have asked yourself, what is next? If we can have f omega plus 1, why not f omega plus 2? What kinds of numbers can we discover that are beyond even the great Graham's number? And how could we possibly grow numbers any faster than we are now? Let's find out in another video. The world of big numbers goes as far as you are willing to go. So please join me for the next video where we explore big numbers.